Welcome to this explainer. Today, we're going to embark on a bit of a builder's journey. We're going to take a look at how to transform rigid, messy code into truly flexible, real-world software architecture. Seriously, if you've ever stared down a massive code base and wondered how the whole thing stays organized without just collapsing like a giant house of cards, well, you are in exactly the right place. Let's get into it.
Okay, let's just dive right into a universal developer headache by asking a seemingly simple question. When you're building a system, is copy-pasting your logic everywhere actually a good idea? Now, spoiler alert here, it might seem like a quick, easy fix at 2 in the morning, but you are absolutely setting yourself up for a world of pain down the line.
Now, what's really interesting about this is how fast a simple university system turns into a massive maintenance nightmare. Let's say we have a student, a lecturer, and an administrator. They all need a name, an ID, an email, and a way to log in, right? Well, if we copy-paste that exact same login logic into 3 totally separate classes, what happens when the security team suddenly asks us to update the password policy? Suddenly, we're tracking down and tweaking that code in 3 different places. That instantly increases the chance of errors, bugs, and just really frustrating inconsistencies. So, to solve this massive headache and stop repeating ourselves, we're going to unlock 4 specific tools in our developer toolkit today: inheritance, abstract classes, interfaces, and finally, polymorphism. All right, let's start with our very first tool for fixing duplicated code, inheritance, also known as the ISA relationship. Before we actually look at the solution in action, we need to understand the mechanics here. Inheritance basically establishes a parent-child relationship. The parent, or the superclass, acts as this single source of truth. It holds the common data, so your specialized subclasses don't have to go and reinvent the wheel every single time. It's essentially a general blueprint that passes down its traits. And this brilliantly illustrates the fix in action. Instead of duplicating everything, we just hoist the name, the email, and those login and logout methods right up into a person-parent class. This means our specialized classes, the student, the lecturer, the admin, can reuse those methods automatically. They literally get all the benefits of the common features without writing the code twice, while still keeping their own unique features, like a student's ID or an administrator's access level. But wait, there is a trap here, and it's a big one. Inheritance only works if there is a strict ISA relationship. I mean, it makes perfect sense. A car is a vehicle, but a car has an engine. That's actually composition, a totally different concept. If you try forcing an engine to inherit from a car just to reuse some code, your system is going to become logically tangled so fast. Recognizing the difference between ISA and HASA is absolutely crucial for designing systems that actually make sense. Okay, moving on to our next tool, abstract classes, our general blueprints. Think about our university system again. You could be a student, or you could be an admin. But actually, scratch that. You literally can't just be a generic person wandering the halls without a defined role. And that is exactly why we use abstract classes. By marking the person class as abstract, we completely prevent the direct creation of these overly general concepts in our software. It exists solely to be a shared blueprint for the child classes that are actually doing the specific work. This idea is incredibly powerful because it lets us define the what, but leaves the how completely up to the specialized child classes. Take an abstract animal class, for example. It can say, hey, all my subclasses must make a sound by defining an abstract make sound method. But it doesn't actually provide the body of the method. It leaves the specific meow or bark or tweet entirely up to the specific cat, dog, or bird subclasses. It enforces the structure, but gives you maximum flexibility. Right, but what happens when completely unrelated things in our system need to share a specific behavior? That brings us to interfaces, the can-do contract. So let's dive into this somewhat bizarre but super common scenario: a bird, a drone, and an airplane. Obviously, they have absolutely no shared family tree. A drone is not an animal. A bird is definitely not a machine. Yet, they all share one can-do capability, the action of flying. By implementing a flyable interface, they're basically all signing a behavioral contract promising the system, hey, I guarantee I can execute a fly method. And you can see how this is a real game changer in everyday business logic. By creating an interface like Payable, totally unrelated objects like a car paying road tax, a phone paying a bill, or a charity accepting a donation can all sign a contract guaranteeing they share the exact same behavior. The system doesn't even need to know what they are. It just needs to know they can accept a payment.
Now, what's really interesting here is how cleanly we can contrast these two blueprints. Abstract classes are kind of like DNA. They're for related items sharing a core identity in an I-is-a relationship, using the extends keyword. Interfaces, on the other hand, well, they're more like a handshake. They are strict behavioral contracts for anything capable of doing the job. It's a can-do capability utilizing the implements keyword, and it safely brings completely unrelated classes together.
Finally, let's head to the grand finale of our builder's journey: polymorphism, the key to truly flexible software design.
The absolutely crucial point here is avoiding this massive, fragile wall of if-else statements that developers just dread every single time a new payment method is added. If your core code constantly has to check, is this cash? Okay, do this. Wait, is it a credit card? Do this instead. Then adding something like a crypto wallet means digging into the very heart of your code and risking breaking the whole shebang. It's a literal nightmare for maintenance.
So the ultimate goal we're chasing here is polymorphism. It's a concept that's perfectly summarized by this simple yet incredibly powerful mantra: one interface, many implementations. The word literally means many forms, and it allows different classes to step up and provide their own unique execution of a single generalized command. And this brilliantly illustrates just how elegant the solution gets in something like a modern food delivery app. Thanks to polymorphism, the central delivery system just calls one simple command, payment.pay. No giant if statements anywhere. It dynamically adapts at runtime whether you used cash, a credit card, or a QR code. You could literally add 20 new payment methods tomorrow, and you wouldn't need to change a single line of that core delivery code. How cool is that? By mastering these tools, you're moving from just typing out basic logic to actually architecting resilient, adaptable software. So as you navigate your favorite apps today, I want you to think about this. How many hidden contracts, general blueprints, and polymorphic calls are running in the background right now, constantly adapting to keep your digital life effortlessly simple? Thanks so much for joining me on this explainer, and keep building brilliant things.